This video is Kinetics 5, and it is titled Rate Law and the Mechanism. Okay, and so earlier on this topic of rate law, I had said that there's no connection between M and N, the individual orders, and A and B, the coefficients in the balanced chemical reaction. The only way that you can figure out M and N is to do that isolation method based on experiments where you're maybe doubling the concentration and then the rate doubles or quadruples like that. That's how you figure out M and N. So it turns out there is some connection between the orders and the coefficients, and it has to do with this topic here, the mechanism of the reaction. So I'll give you a couple of examples after a little bit of discussion here to show you what I mean by that. So first we want to define a few terms. This first subtopic or subheading would be elementary reactions. Okay, so I'll just give you an example here. And it is our peroxide reaction, H2O2 plus I minus. I think we've looked at this one before. Forming two waters plus O2 plus I minus. So I'm going to put that in the box. And I'm going to call this the overall reaction. Okay, now we can talk about the mechanism for this reaction or the mechanistic steps. Which are also called elementary reactions. Okay, and in this case, think about the left-hand side, you have two peroxide molecules and an iodide. So we could say the first elementary reaction or first mechanistic step would be where one peroxide molecule reacts with iodide. Water is formed. If you look at the peroxide, you could see how one oxygen could be expelled there and react with the iodide. And so the other product is IO minus. That is hypoiodite. And so then the IO that's formed, notice that it is not in the overall reaction, and that's going to be considered to be the intermediate. So it's going to disappear in the next step where you take the second peroxide from the left hand of the overall reaction. It'll react with that intermediate IO minus. The product of that will be water plus O2 plus I minus. Okay, so this is step 1, and this is step 2 in the mechanism. Now, one of the properties of this is that when you add up the individual steps, you should get the overall reaction. And you can see here that the IO minus will cancel. And actually, that's the only thing that has to happen. So when you add them, you're going to get two peroxides plus I minus forms two waters plus O2 plus I minus. So your mechanism that you propose has to be consistent with the overall reaction. So in this case, we've got two interesting species that are occurring. The one that I just mentioned, this one, that is the intermediate. But also you have something else here. The iodide is on the left-hand side of the first step, and it ends up on the right-hand side of the second step. This is going to be called the catalyst. So in other words, hold on, let me fix this one thing here. There we go. So the catalyst, notice, is given in the overall reaction. You see it in both the left and the right-hand side. So that's kind of a characteristic of the catalyst. If you just have peroxide by itself, it is not going to spontaneously decompose to form water and O2. You might know that if you've ever worked with contact lens solution containing peroxide, right? You have to have some kind of catalyst to get this peroxide to break down. And peroxide can sit on the shelf for years without decomposing. So that's a thermodynamic issue as well as a kinetic issue. But if it's, thermodynamically it's stable to do this, but there are kinetic reasons why it doesn't happen, involving the activation energy, which is the discussion of the last kinetics video 6. But if you put it in the presence of a catalyst, then it goes. You can decompose peroxide. And the convention is to put it on the left and show that it's still there. That's one of the characteristics of the catalyst, that you add it, but in the end it is not consumed. So in terms of the mechanism, again, the catalyst comes into play into both of the steps. And then what's new here is the intermediate. So the intermediate might last a second, it might last a nanosecond, picosecond, anywhere in between. It could be that it actually builds up and it becomes the rate determining step for the reaction. So in other words, the rate of the reaction depends on the concentration of the intermediate. But other times it's so quick it doesn't even matter. But sometimes then you can study it. You can show spectroscopically that that's the compound or the molecule that's that is the intermediate. Sometimes you postulate it and maybe you get proof for it 20 years later, something like that. But in any event, this is a mechanism that's consistent with the overall. We're taking a guess that it's IO minus that is involved in this, but we may not know 100% until we find a way to discover it. All right, so there's all of that. Then what else here? I guess I'll say that the property of the catalyst is that it speeds up the rate of the reaction, but is not consumed during the reaction. Alrighty, now when we look at each one of those elementary reactions, oftentimes we describe it in terms of molecularity, and it's a number, 1, 2, 3, molecularity, and not the same as the order. It's just a way to describe steps in the mechanism. And so the definition here is going to be the number of molecules on the reactant side of an elementary reaction. And we use the notation unimolecular, and it's given a number 1. That's not a negative there. I'll just say 1. Bimolecular, it's going to be 2. Termolecular is 3. And termolecular means that 3 molecules come together, or 3 species, 3 reactant molecules come together, and they collide, energy exchange, bonds form, bonds broken, and then the product is formed. So the probability of a termolecular reaction is kind of low because for 3 molecules to come together at once, it's just less probable, especially in the gas phase. All right, now just some examples for molecularity, and these are for the steps in the mechanism. And so here's an example of a unimolecular step or reaction step. And in this case, oh, there it is. Sorry, the unimolecular step. So in this case, you've got some ozone. Maybe it's sitting in the upper atmosphere, so it's been irradiated with high energy light, or maybe some high energy neutrons, that kind of thing, that's caused it to be excited. So the star here tells you that it's ozone that's got a little bit of extra energy. Usually that happens when the electrons absorb the energy and get promoted into some higher orbital state. All right, so here's ozone out there. It's very excited. It's all by itself. And then it will spontaneously decompose to form O2 and O. So it's a unimolecular step because there's just one molecule on the left-hand side of the reaction. All right, an example for a bimolecular. This one, excuse me. This one would be NO2 plus NO2 forms NO3 plus NO. So in this case, these 2 molecules combine to form what's called the activated complex, meaning that when they come together, usually they've got some high energy associated with their collision energy, and that energy gets absorbed by the molecules. They come together, and then they form this complex where the NO bonds are starting to break and the new NO bonds are starting to form, and just this little transient period in the progression of the reaction sequence. A little bit of stability associated with an activated complex. But anyway, that's the subject of the next and last kinetics video. In this case, we're just looking at the fact that there are 2 molecules on the left-hand side here, and that is a bimolecular step. All right, so then let me go to the next slide. I already have it open. Whoops, what happened? I lost my thing. There. Get rid of that. Okay. So here we can write a rate equation for each elementary reaction. So if you have an example where A forms B plus C, you can write a rate law for this step. And you'd say rate is equal to K times the concentration of A. And here's where we're going to take the coefficient 1, and it's going to become the power 1. So the orders or order in this example for A is equal to the coefficient for A in the balanced reaction for the elementary steps only. You cannot do this for the overall. Okay. Then here's another example. If you have A, whoops, well, okay, we'll make it like that. 2A plus B forms some product C. We can write a rate law for this. It's going to be K times A squared times B to the first power. So it's in terms of what's on the left-hand side of the elementary step, and the order equals the numerical value for the coefficient. All right, and we could keep going with that, but I think you get the idea there. All right, so I want to show you now how to use all this information about the mechanisms and the rate laws for each step and come up with information about the overall reaction. So there's going to be two examples here. The first one's a lot easier than the second. So for this we have 2 NO2s plus F2 forms 2 NO2F molecules. This is going to be the overall reaction, and everything you do has to be consistent with the overall reaction. I like to put it in a box, and in this example it's known to be second order overall. So it observes second order kinetics. And it is known from your doubling experiments that rate is equal to K times NO2 first power times F2. So that is an example of a second order reaction overall. It's first order in NO2 and first order in F2. Okay, so the question is, what is the mechanism consistent with that? You just have to guess, or on our tests it'll be given and you'll have to work with it. But what is the mechanism? If you're doing an experiment with a new reaction in the lab, you have to make a guess, and then you have to see if it not only consistent, but if it's true. So you have to actually try to detect your intermediates. Okay, so what if we did a guess here? Let's say we said there's just one step here, so the elementary reaction is the overall reaction, and you have 2 NO2s plus F2, all three of them colliding, and the reaction takes place with 3 molecules at the same time, and NO2F. So if that were the case, then the rate law for this elementary reaction, which happens to be the overall reaction, would be rate equals K times NO2 times NO2, which is NO2 squared, and then times F2. So, is it correct? The answer is no, because this is third order. And it's inconsistent with the experiment. All right, so that's no good. So then we can take another guess. This one works. This is the correct one. And this is going to be a mechanism with an initial slow step. And you write out the steps for the mechanism. This would be NO2, one of the NO2s reacting with F2. And you draw an arrow. You're going to label the rate constant for this first step as K1. Then you have NO2F as the product plus F. F is highly reactive, so a good guess that that's going to be an intermediate. So we can label this one as the slow step. And we're going to find out the rate of the reaction depends on the rate of the slow step. So, but you've got this intermediate, the F intermediate on the right here. That thing has to disappear. And so the second NO2 molecule will react with F. The second step has a rate constant K2. And then there'll be a NO2F formed again. And is that consistent with the overall? Yes, 2 NO2s plus F2 forms 2 NO2F. This step is fast. All right, so we're going to use the idea, I mentioned it already, that the rate of the reaction depends on the rate of the slow step. I'm going to write this down because it's very important. So the rate of the reaction, the overall reaction, equals the rate of the slow step. And the analogy might be if you're driving maybe on the freeway. I live in Thousand Oaks, and I teach in Northridge, so it's a long drive every day. I tend to drive pretty fast, and let's say I'm clipping along 75 miles an hour as usual, and all of a sudden there's a car accident, and we come to a standstill for a little while. Let's say it takes 2 hours to get through the accident scene, and then when I get on the other side, I start speeding up again, and I finish my trip to Northridge. So, it takes 20 minutes on either side, but there's a 2 or 3 hour wait trying to get through these, quote, slow part of the trip, or the slow step if it were a chemical reaction. So you could say, okay, the time it takes me to get to Northridge, or the rate, at which I get there, has to do more with the slow step than the fast parts. And with chemical reactions, some of them are orders of magnitude faster than others. So it's a little bit more obvious how it would work if it were a chemical reaction. But that's the idea. It's going to take all the time to get through the slow step. As soon as the product species are formed in the slow step, as soon as they're formed, then they're quickly going to go on to form, in the second step, they'll go on to form the final product. So we use this as a very good rule, and we can immediately say then that for this mechanism with 2 steps, the first step is going to be the rate determining step. So for this case, step 1 is the rate determining step. So if that's the case, then we can say the rate for the first step is equal to K1 times NO2 to the first power, because that's the coefficient, times F2 to the first power. And then this has to be equal to the rate of the slow step, which is the rate of the overall reaction. So in the end, you drop all that 1s and 2s, and you say the rate of the overall reaction, and you drop the 1 on the rate constant K, and then you come up with this as your final answer. So this is the easy one. You can find that slow step and say that has to be equal to the rate of the reaction, and then write it out. Now, is this consistent with the fact that from experiment it's a second order reaction? Yes, it is. So this is an acceptable mechanism. And we're done. That's the first example there. Excuse my throat here. Drinking tea. Okay, so then the next step is the hard one. Nobody likes it, but it's actually kind of fun. Maybe I'll start a new page for that. All right, this is a different kind of mechanism here. Mechanism with an initial fast step. And in this case, it's an equilibrium step as well. So mechanism with an initial fast, I'll say equilibrium step. Okay, that's the title here. Okay, so this one is our old friend 2N2O5 in the gas phase. I've been leaving off the phase, and I don't need it here. 4NO2 in the gas phase plus O2 in the gas phase. You know, if you think about in the gas phase, you can maybe imagine the collisions and how things would come together to react, perhaps. So for this one, from experiment, and we know this, we actually spent a lot of time on this, this is a first order reaction. Okay, and what else do we know? That's about it. So then we can come up with a mechanism for it, guess it, and maybe based on a few things we know about these types of reactions, maybe that would help us make a good guess. And if we did that, we could come up with N2O5. We'll leave off the phases here. And we can let this be an equilibrium step. We're going to have K1 associated with the forward reaction and K minus 1 associated with the reverse reaction. The product of the forward reaction is NO2 plus NO3. So we're going to specify here that this is fast and there is an equilibrium. Now, once this equilibrium is established, we're going to have both reactant and products present. And the NO2 product in this step will react with the NO3 product. Instead of going backwards to form N2O5, it's going to go forwards to form NO plus NO2 plus O2. This is a slow step that's characterized by rate constant K2. So that's our second step. Sometimes you see the equilibrium constants being maybe K1 and K2, then this one would be K3. Sometimes you see K forward and K reverse and then K2. So there's a couple different ways to do that. It doesn't really matter. All right, and then you have the NO3 product reacting with the NO produced in the second step to form two NO2s. And that's characterized by K3. And that one is fast. All right, so there's 3 steps in this mechanism. The first one is equilibrium. And if you were going to add them up to get the overall, just to check to make sure everything works, you actually have to, I'm not going to write it down, but I'll show you. You have to multiply this first reaction times 2. So it has to be 2 here, 2 here, and 2 here. There's no problem with writing this thing twice. There's millions of molecules in the system, so you can do that. But you'd have to have 2 in order to have things cancel correctly in the other parts of the mechanism so that it adds up correctly to get the overall. You can play with it on your own and see that that's true. Okay, so then we could perhaps think that the rate of the slow step is the rate of the overall reaction, and so we could say rate of the slow step will be equal to K2 times NO2 times NO3. All right, and we know from experiment that this is first order. So there's nothing wrong with our logic. We know the rate of the slow step is the rate of the reaction, but it's not in the right form. So we know also that we have NO2 in our rate law, and we have NO2 here, but we do not have NO3, which is in the slow step rate law. That is not part of this overall reaction. So that's what's wrong here. The NO3 is not in the overall. So we have to use more information from equilibrium. We know that the rate of the forward reaction equals the rate of the reverse reaction, and that's what we're going to use here. So in other words, this is rule 1. There's another rule that we need, and that rule is that for an equilibrium step, mechanistic step, the rate of the forward reaction equals the rate of the reverse reaction. Actually, this is something we're going to talk about later in the equilibrium chapter. In the kinetics chapter, and I'll show you how you can actually derive the equilibrium constant from it. But the rule that arises out of all that is this one right here. So we'll use it first. Okay, so for an equilibrium step, that would be our first one, the rate of the forward reaction equals the rate of the reverse reaction. And before I write it down, I'll point to it. The rate of the forward reaction is going to be K1 times the concentration of N2O5 to the first power. That will be equal to the rate of the reverse reaction, which will be K minus 1 times NO2 raised to the first power times NO3 concentration raised to the first power. So when we write rate laws for the mechanistic steps, it's always in terms of the reactant. So the rate of the second step would be K2 times NO2 to the first power times NO3 to the first power. The rate for the third step would be K3 times NO3 to the first power times NO to the first power. So it's always in terms of the reactants, what's on the left. But in this case, you've got reactions going in both directions. So you could say K1 times what's on the left. But if you actually broke this equilibrium into two reactions, the second reaction would be NO2 plus NO3 is forming N2O5. And so you could think of this as being on the left and not inconsistent with everything else that we're doing here. All right, if you don't like that, you just go ahead and follow. That's one of the hard steps. So you just follow what I'm doing. So for the equilibrium step, we're going to say the rate of the forward reaction is K1 times N2O5, and then the rate of the reverse reaction is going to be K minus 1 times NO2 times NO3 concentrations. All right, why do we care about that? Because back over here, we've got this problem with our rate law. There's nothing wrong with saying the rate of the reaction equals the rate of the slow step. The problem is that when you write the rate of the slow step for this example, you've got an intermediate. The NO3 is an intermediate, is not in the overall reaction. So what we're going to do is use this second equation. So in other words, you've got two equations with one unknown here. So we're going to solve for NO3 from our second equation, and we're going to plug it in here so that the rate of the slow step will then be in terms of what's in the box. what's in the components of the overall reaction. It could be reactants or products, it doesn't really matter. All right, so then what we're going to do here is solve for NO3, nitrogen trioxide. That'll be equal to K1 times N2O5 divided by K minus 1 times NO2, right? Solve for NO3. The NO3 then will be substituted into the NO3 for the rate of the slow step. So when we do that, then we have the rate of the reaction equals the rate of the slow step, no difference there. But this is going to be equal to K2 times NO2 times this, which is K1 times N2O5 divided by K minus 1 times NO2. Seems difficult, but watch what happens here. The NO2s cancel, and then we're going to get to the rate of the reaction. The overall reaction is going to be K2 times K1 divided by K minus 1 times N2O5, and it's first order. This is consistent. This mechanism is consistent with experiment. Experimentally, we know it's a first order reaction. The last part here is to take this combination of constants and say K2 times K1 divided by K minus 1 is equal to K. And if you think about it, K's are just numbers. So maybe K2 is 100, maybe K1 is 10. So that would be 1,000 in the numerator. Maybe we're dividing by 0.1 for K minus 1, so that would be 10,000. And so it's just a number. If you calculate the numbers on the left, you end up with a new number, and we're going to call that K. So that's okay. We can do that. And we're going to say the rate then is equal to K times N2O5 to the first power. That is absolutely consistent with the rate law that's observed in the lab. All right, that is a difficult problem, and maybe you watch the video a couple of times. And there's going to be a problem like this in the group activity. There'll be some more problems like this in your book. It's very typical to see these mechanisms where you have an equilibrium step and then a different one is a slow step. So you want to make sure that you master both types, type 1 and type 2, for your going forward, getting ready for your exams and your quizzes. All right, I think that's it on mechanisms. One more video to go on kinetics.